right, welcome ladies and gentlemen to the Empirical Formula review. Empirical formula is something that, as a term, you've seen it before in Regents Chemistry, but you might not have gone through how to calculate it in Regents Chemistry. It is something, however, that we're going to be doing many times in AP Chemistry, so it's worthwhile having this as a type of problem to make sure you feel very comfortable doing this. So empirical formula, hopefully you do remember that it is defined as the lowest molar ratio of elements in a compound, meaning like the most reduced down that you can get the subscripts. You know, what is the lowest ratio of the different elements in a compound? In terms of calculating that empirical formula from percent composition data, which is a very common type of problem, I've written up here the steps of what you need to do. The first thing that you should do is assume that because it's based on percents, and percents are out of 100, assume that you have a 100-gram sample. What this allows you to do is to change all the percents into grams. So if it says 50% oxygen, you'd say 50 grams of oxygen. Next, you're going to have that gut check reaction. If we have grams in AP chemistry, what do? You turn it into moles. Empirical formula is the lowest mole ratio. So our second step after assuming 100 grams is going to be not looking at the mass data, but turning that mass data into mole data, figuring out how many moles of each element we have, because that's what we need. It's the lowest molar ratio. Once you figure out how many moles you have, this does essentially give you the ratio, but it might not be whole numbers. So we've got to get it into whole numbers. The way that we do that is to find the smallest number of moles between all the elements and divide all the elements by that smallest number. Where we're keeping the ratio intact, we're just maybe turning it from possibly awkward decimals into hopefully nicer values. If after this step you still don't have all integers, you're going to need to multiply by a common number in order to get all whole numbers, because as you know, we can't have decimals as subscripts, and they have to be whole numbers. So sample problem. First up, determine the empirical formula of a compound that is 89.14% gold and 10.86% oxygen by mass. All right, so they give us percent composition data. We don't really want percent composition, we want mass data. So we're going to start by saying instead of 89.14%, it's 89.14 grams of gold and 10.86 grams of oxygen. But grams are useless to us in chemistry. The only reason that grams are at all useful is because they allow us to turn grams into moles. It's really moles where we get all our interesting and significant information from. So that's going to be our next step, turn grams into moles. We do that by dividing by the gram formula mass. Dimensional analysis, grams cancel, we get moles. Gold, look up gold, that is 197.0 grams for 1 mole of gold. Grams cancels. So we're getting moles of each because empirical formula is the lowest molar ratio. So we go through this, we get 0.679 moles of oxygen and 0.452 moles of gold. This right there is your ratio, 0.452 to 0.679. Well, you know, that's great, but that's not a terribly apparent ratio in terms of integer values. So we're going to need to do a little bit more work to figure out what the integer ratio is between these two elements. So that brings in our next step. It's not apparent essentially what the subscripts are from this, so we need to divide everything by the smaller number. Well, 0.452 is the smaller number. So divide both of them by the smaller number. That first one gives us 1 for the gold. Now, it's this step where you can approximate. This is going to give us about 1.5. So this right here, this is the ratio between gold and oxygen. Right, gold 1, oxygen 1.5. But that doesn't cut it yet. You cannot have that as your subscript. So we're going to multiply the subscripts by something, both of them by the same thing, so that we can get integers for both of them, and that's 2. Because if we multiply 2 by 1.5, then we get 3 for the oxygen and 2 for the gold. So our empirical formula right there is AU2O3. So again, we got moles of each. We got the 0.452 moles of the gold, 0.679 moles of the oxygen. This is a molar ratio, but it's not a very nice one. The way we make it into a nicer one is dividing by the lower number of moles. And then it's at that point that we can start approximating and then start turning it into something that is a bit of a nicer number. Determine the empirical formula of a compound that is 21.2% nitrogen, 6.1% hydrogen, 24.2% sulfur, and 48.5% oxygen. There are 4 elements in this compound. Big whoop, doesn't matter. We're going to do the exact same thing, so we have 4 elements instead of 2. Who cares? It's the same exact type of problem. Going to start the exact same way. 21.2% nitrogen, we're not going to say percent, we're going to say grams. And we're going to turn it into moles. Right, nitrogen 14.0. This is not diatomic nitrogen. This is not nitrogen gas. This is nitrogen, elemental nitrogen that is in a compound. So we are using the atomic weight right off of the periodic table. Hydrogen, not 6.1%. We're going to say 6.1 grams. Gut check reaction, AP chemistry. You see grams, you turn it into moles. 1 gram per mole hydrogen. Next up, sulfur, 24.2%, not percent, grams. Please, ladies and gentlemen, have some self-respect. Sulfur is not 32. It is 32.1. Take it out to the 10th, please. Minimum. If you want to take it to the 100th, great, go for it. But do not take it to the ones. And then last, the oxygen, running out of room here. But we're doing the same thing, dividing by 16 grams for 1 mole of oxygen. We're going to figure out how many moles of each one we have. That is going to be on our way to telling us the lowest molar ratio. So I do this math. I get 1.514 moles of N, 6.1 moles of H. That's easy enough. Sulfur is 0.753, and the oxygen is 3.031. Don't round. Do not round the number of moles. If you round the number of moles, then that can throw your mole ratio off. So you want to keep some decimals there. You'll notice I am taking them out 3 places. That's not our final answer. So we're keeping those numbers there. Now, at this point, you may or may not be able to see the mole ratio. If you do see the mole ratio, great. You can kind of just go straight to the empirical formula, meaning the integer mole ratio. If you don't see the mole ratio at this point, then you want to go to the next step, which is locating the smallest number of moles, which is the sulfur, and you're going to divide every value by that, because that's how we get ratios realistically if we have decimal information. So we're going to divide everything by 0.753. And when we do that, here's where we're going to approximate. This turns into approximately 2 for the nitrogen, approximately 8 for the hydrogen. That's obviously 1. It's not approximate, it is 1 for the sulfur. And the oxygen is approximately 4. Now these are integer values, so we don't need to do anything additional in terms of multiplying. So we can just go straight to the empirical formula, N2H8S1. You don't need to write in the 1, and O4. N2H8SO4. In fact, this compound is actually ammonium sulfate, the N2H8. It comes from the 2 ammonium ions that we have in the compound. So empirical formula, lowest mole ratio. You turn percents, you assume a 100 gram sample, turn percent into grams, gut check reaction, AP chemistry, you see grams, you turn it into moles, because this is empirical formula. We want the lowest mole ratio. That's our second step, we get moles. Once you get moles, then start thinking about what the ratio is between all those moles. If it's not apparent to you at first sight, all you do is you find the smallest number of moles, you divide every mole value by that smallest number of moles, and then and then that will get you your ratio. Turn it into whole numbers, because we can't have decimals as subscripts, and there you go, you have your empirical formula.